Hi, Giacomo. Are you
Hi.
listening? Yes?
Yeah, everything's fine.
Yes? Okay. So, hello, everyone. So, first I will talk in Portuguese. So, olá, todo mundo. Estou de volta aqui só para apresentar o Giacomo. Ainda estou na minha licença maternidade, mas vim aqui prestigiar o nosso palestrante de hoje. E, então, eu vou passar para inglês para apresentar o Giacomo, que o Giacomo vai fazer a apresentação dele em inglês. Então, vou fazer um breve resumo da trajetória do Giacomo para vocês. E eu tenho só um aviso, na verdade, o Giacomo tem um imprevisto, surgiu um imprevisto para ele hoje. Então, o colóquio vai ter que terminar às 11h30, ele vai precisar sair na sequência, tá? Então, ele vai fazer uma apresentação curta, de uns 40 minutos, aí a gente tem um tempo ainda para perguntas, beleza? So, okay, so now I switch to English. So I will do a very brief presentation of Giacomo. Giacomo has been a collaborator here at the Grupo de Ótica in the Institute. And so some people here in the audience already know him, and I will do a very brief presentation now. So Dr. Giacomo Roati did his PhD in 2003 at the University of Trento, working with Professor Massimo Inguscio at Lens in Florence, where he studied quantum degenerate mixtures of sodium and potassium. Later, he did some short postdocs, including one at MIT, and he returned to Florence, where he started an experiment with degenerate Fermi gases of lithium-6, for which he received an ERC grant in 2012. Since 2018, Giacomo is a director of research of Lens, and he has realized very important studies on quantum transport phenomena in strong correlated Fermi gases across the BC-BCS crossover. Today, he will do a brief introduction to the field of ultracold atomic matter, and I think I can give the word to Giacomo now. So thank you very much, Giacomo, for accepting our invitation. And yes, you can share your screen.
Okay, now I will put the full screen.
You.
First of all, I would like to thank Patricia for the invitation. And I have seen while I was looking at the audience, a lot of good friends. I want to say hello to Vanderlei and saying that I miss there a lot. And so I will try to come back now after this pandemic as it's finished, at least in a good approximation. So as Pat was saying today, I apologize for this, but I have an appointment at 4:30 that is impossible that I could cancel. Anyway, I'm going to give you, I was asked to give an introduction that probably will be basic for some of the people, but since it's for students, I will be quite easy in approaching ultra-cold gases. But of course, then I will be happy to answer to any question on more detailed stuff. Okay, so I will give you some idea about how it's possible to control and produce ultra-cold system. And the first thing that I want to start to ask and to answer, in fact, is what does it mean when we say ultra-cold? Well, when we say ultra-cold, we say something that, in fact, corresponds to the coldest matter in the universe, because ultra-cold atoms lies in this temperature scale at the level of nanokelvins or microkelvin, typically nanokelvin, for example, in the case of Bose-Einstein condensate and superfluid Fermi gases. So there is nothing else in the universe that is such cold. Just to give, again, maybe it's stupid, but I think that to give a visualization of what does it mean so cold, if we consider, for example, a room of like 20-meter length, then of course particle or molecules at room temperature will travel this in more or less 1/10 of seconds, while if I am able to slow down this particle in some way to such low temperature, this corresponds to velocity of some millimeter per second. This means that it will take almost 1 hour to travel all across the room. So this is just to give a visualization of what happens, when you cool down systems such, at least in the classical, or from the classical cinematic point of view. Well, then the second question that we can ask ourselves is why do I need to go so cold, and why do I go so cold? Well, Patricia told me that some of you started just now the courses in physics, so maybe this is something that you did not touch, but you are going to see that, of course, from the quantum mechanical point of view, you can associate to any particle a wave packet, which extension, in fact, is then indicated by a lambda, a wavelength that is called the Broglie wavelength. And this quantity is, in fact, related actually to the inverse of the square root of the temperature. And just to give you an example of what does it mean, I pick up one system that is typically cooled down in laboratories like the one in Vanderlei, but in other places in the world, rubidium. Well, if I consider a rubidium atom at 300 Kelvin and I do a simple calculation, typically you have that the Broglie wavelength are of the order of 10 to the minus 11 meter. But if I am able in some way to cool down the system to around 100 nanokelvin, when typically phase transition to Bose-Einstein condensate happens, well, in this ultra-cold system, then you will see that the de Broglie wavelength is still quite small, but becomes compatible to something that you can imagine to see and to measure, that is of the order of 1 micron. So that means that you can really tune, if you want, or you can increase the wave nature of the particle, just decreasing the temperature, for example. Then the question is that what is happening when this happens, and why, I mean, is important to, why is it important to cool down the system? So I'm sorry, I mean, maybe this is too basic, but just to give you a visualization of what can happen. Here I consider like 3 particles, and again, I can associate to these 3 particles a wave packet, and the extension of this wave packet is the Broglie wavelength. These particles are suppose in an ensemble, a 3-dimensional example can be, and the average distance between the particle I indicated here with D. Well, suppose that now I cool down the system, and cooling down the system, what happens is that, as I said before, the de Broglie wavelength starts to increase, and there will be a point in which the de Broglie wavelength becomes comparable with the mean interparticle spacing. And again, if you do a small, sorry, I have to remove this from my screen. Okay, if you do a simple math, you will see that this temperature corresponds to something that is inverse proportional to the mass of the particle to the density of the system, to the 2/3 in 3D. Then if I cool down even more, what happens is that the wave function or the wave packet of the particles start to interfere. And from this point of view, you can imagine that it will be quite complicated to distinguish which contribution is which from which particle, since these are completely interfering. Like you can consider this, supposing to throw stone in a lake, you will see that the waves start to interfere, and it will be very complicated to see which components is due to which particle. While here you can clearly identify which particle is which. And this, in some sense, from the point of view of the statistical mechanics, corresponds to the change between a description that can be effective using Boltzmann or classical statistics to something that is more, that is at the end what one has to use, that is the quantum statistics, in which, of course, the quantum nature of the particle become important. Okay, so why ultra-cold atoms are important or are interesting? Okay, first of all, the first message that I want to give to you is that these systems are very special. Actually, the same Bose-Einstein condensate in ultra-cold gases is a metal stable state, because of course the ground state you would expect to be a solid at this temperature. But anyway, the system keep the very dilutinous nature, and in particular they are 1,000,000 times thinner than the air that you are breathing in the room where you are. So we are talking about density of the order of 10 to the 12, 10 to the 13 at maximum atom per centimeter cube. Of course, I said that these are also very cold and are much colder than the space, that is at the order of Kelvin, like 1,000,000 times. And when I say very tunable, I will enter in some discussion in this later, means that in particular you can control even the interaction between the particles with some trick. And in general, all the experimental parameters are controllable. So, and this is something very important, of course, from the experimental point of view, because all the details are under control. In particular, you can tune, and this may be something that you don't know, but of course, I will enter in some detail later about the fermions and boson nature, but you can tune in the statistics between the particle. So you can study Fermi system, Bose system, or you can combine with the two. You can control the density, so the number of particles, even the spin, the pseudo spin in some sense, but the spin of the particle, and the interaction between the particle. As said, of course, you can control the temperature, and very, very importantly, you can control the potential, the trapping potential where these atoms are in some sense contained. And this is due to the fact that now, nowadays, most of the potential are done by laser light. And indeed, light plays a significant role in all the history of ultracold gases, because with the atoms, as I'm going to tell you very naively, but I hope effectively, you can cool the system, then you can trap the system, and then, of course, you can image the system. Okay, image means that you can do a sort of photo, actually a picture of the atoms, and in a way that you can extract from a picture like this, that is taken on a CCD camera, all the important feature of the cloud, for example, the temperature and the number of particles that it has. Okay, so that is more or less the first message that I think is important. So we are dealing with the coldest matter of all the universe. So there is nothing coldest than this. And when the system becomes cold, again, I was saying to you at the beginning, quantum statistics start to be the right way, and quantum mechanics, of course, to describe the behavior, for example, the dynamics. And here, we can just differentiate between two classes of particles. Bosonic particles will have an integer spin that will follow a distribution function that is the so-called Bose-Einstein statistics. And on the other side, for particles that are half-integer spin, that are called fermions, you will have a Fermi distribution, or Fermi-Dirac distribution function. This is just the way in which you will allocate the particle in some energy state or energy levels of, for example, a potential, okay? And just to tell you, of course, they seem quite similar, except for this sign. And this is a very nice example in which one sign can make these things very, very different, of course. Well, just to give you let's say some description or some indication of what I mean. If I consider now, for example, an harmonic potential, so a container that is harmonic and with some harmonic level, and again, I don't know how much you know about, but simply you consider like a container with many levels in which you can put the particles. In the case of bosons, then you can bring all the particles occupying the lowest energy, single particle energy state of this potential. In the other case, when you consider fermions, this is not possible, for there is a Pauli principle that will inhibit this. And you have to pile up all the particles, filling up all the levels up to the last level that is called the Fermi energy level. Well, to say in a sort of a funny way, I would say that for bosonic particles, there is a statistical attraction between the particles, while if I consider fermions, there is a statistical repulsion between the particles, when I consider, of course, identical fermions. And these are examples that probably you can, I did not have all that you have in nature, of course. Example of bosonic particles, of course, in both cases, I have atomic classes, but then in case of boson, you have photons, you have phonons, you have helium-4, for example. Here, of course, you have electrons, nuclei, white dwarfs, and helium-3. Of course, then you have superconductors and so on and so. But just these are some examples of these two categories. Well, the first point, and this in fact was one of the motivations why quite a bit of time ago I started to study this kind of physics from the experimental point of view, that I was very curious to understand that people were telling me how laser can cool atoms, because typically you can think that laser is associated to, at the level of industrial, for example, exploitation, to something that heat and can cut. How is possible that laser can cool the atoms? Well, without entering too much in the detail, I think that what is important here is that atoms that move, for example, in the space, will interact with photons. And during the photons and atom interaction, there will be, of course, absorption, and there will be an exchange of momentum between the photons, and atoms. Well, this is just a pictorial point of view, but what happens is that, of course, atoms will absorb, and the absorption will give a kick in the opposite direction where the photons is absorbed, but then will re-emit the photons, and the re-emission will be isotropic in the space. Okay, so I will not enter too much in the detail about Doppler and other kind of mechanisms, but this is just to give you an idea. It's like to consider like really many small particles that are hitting this particle, that is the atoms. In some way, they will remove momentum from the particle itself, from the atom. Of course, this you can think that could be something that is not very efficient, but since lasers is composed by many photons that have almost the same nature because they live in the same electromagnetic mode, you will see that the atoms will absorb and re-emit many photons. You can think like 10 to the 6 per second. And this will be able to reduce very heavily the temperature of the particle. And just to give you an idea, maybe for students, the deceleration that you can estimate is of the order of is 10,000 G. When I consider, for example, just an example that if you take a motorbike, the one that run in the GP competition, this typically is a couple of G. So you will see that how a poor atom will be subjected to a very strong deceleration due to the interaction with photon light. Okay, in this way, typically people reach temperature that are of the order of microkelvin, okay? And there are some limitations, of course, in this technique, but just take into account that you start with a cloud of atoms at 300 Kelvin, and at the end, after like a few milliseconds, you will arrive to atoms that have temperature of the order of tens of microseconds, tens of microkelvin. But this still, if you do go to calculate or to estimate, which is for the given density that you have, the ratio between the de Broglie wavelength and the distance between the particle, we are still far from the regime in which the wave function or the wave packet will massively interfere. So you need to cool down more. And to cool down more, okay, this, sorry, is an example of the mod. Sorry, this I had a problem with the slide, but this is an example of a magneto-optical trap. These are the atoms cooled down by light. So to cool down more, you have to transfer the atoms inside a magnetic trap, a magnetic potential, for example. And here, I don't know, again, how much you know about this, but just the message that I want to give you is that the spin of the atom is then coupled with the magnetic field. In this case, it's a spatial varying magnetic field. And at the end, the atoms that are trapped, if they interact with the magnetic field, will just, in some way, oscillate inside this trap. Okay, then this is what happened up to like 10 years ago. Now there are other kind of trap in which you can cool actually and trap the atoms, and these are done just by laser light. And these are two kinds of trap that you can have in this case. You can have such cool red traps in which the atoms are trapped in the maximum of the intensity of the light, or you have blue trap in which the atoms are expelled from the maximum region of intensity of the laser beam. But just to give you the flavor, is possible using the combination of the induced electric dipole moment and an electric field that is varying in the space to create this kind of trap in which the atoms can be trapped after they are pre-cooled in this by the laser cooling technique. Well, just to give you some idea of some advantages between or differences between the two traps, of course, in the case of a magnetic trap, you have that you are constrained only to some internal state of the atom. So not all the internal state of the atom are trappable, and I will not enter too much in the detail. While in the case of trap done by laser light, you can trap almost all the spin state. And then, of course, the fact that you use an electric or a laser beam that you can shape in different geometries, then this gives you the possibility to design and tailor different optical potential. And this I will give you at the end some example. Just to start with that, you have to consider that since I use laser beam, and laser beam can interfere, for example, if they are retroreflected, for example, from a mirror, using laser light, you can create optical potential that in some way resemble what happened in a solid state or in a crystal. For example, if I take 3 pairs of laser beam that are retroreflected, I will just create the so-called 3-dimensional optical lattice, and the atoms, the cold atoms, will just sit. They can really sit one by one, but they can sit even more than one in each of these blue dots, resembling this, in this case, a crystal, okay? Or you can create 1-dimensional geometries in which instead I will use only one laser beam, and I will constrain this, the atoms will live in this 2-dimensional layer, and this is called one-dimensional optical lattice. Or if I use two pairs of beam, I create a two-dimensional optical lattice, and at the end, the atoms will be constrained to live in one-dimensional tube. So just to give you the flavor of this, it means that in principle, by playing with the number of laser beam that I imprint on the cold sample, then I can pass from a three-dimensional system, actually one-dimensional system means that is like, sorry, zero-dimensional system that is a three-dimensional optical lattice. I can study two-dimensional system using a one-dimensional optical lattice, or I can use study one-dimensional system if I use two-dimensional optical lattice. So it means that I can change the geometry and then the physics heavily of the system by changing the number of laser beam that I superimpose on the system. Well, then the advantage, of course, to use in general, this kind of container relies on the fact that then I can implement additional cooling technique. And to do that, in fact, you have just to consider that the comparison to what you do, and this is a typical example that people saying these things say to the audience, to what you do when you want to cool down a cup of coffee or a cup of tea. You just to blow out the hottest particle, the one that arrives at the surface, or you just wait that this happen by themselves, but you blow out these particles, and what happens is that the system of the remaining particle will thermalize using, elastic collision between the particles, and this means that at the end, your coffee or your tea will be, of course, naturally cooled. This, of course, you cannot blow out atoms from our system, but what you can do, with your breath, but what you can do is to use microwave or radio frequency photons, in fact, to expel from the trap only the atoms that are the hottest. At the end, what is happening is that the atoms that remain in the trap will cool down and they can reach ultra-cold temperature. Well, as we said at the beginning, because this is important for you to see how this happens, is that, of course, once that you cool down this gas, you want to know which is the temperature and which are the number of particles, so the density that you have achieved in your system. And this happens, again, using absorption imaging. So you just go to see and you measure how much the system absorbs the light that is given by an extra laser that is resonant with some of the laser of the atom transition. Then on a CCD camera, you will see, this is in a full scale, anyway, it is in a color scale, sorry, the density profile that you see, you will see something that is like this. You will see some very dense region in the center, and then you will have the density of the cloud will decrease. And this typically you do in time of flight. So you have your container, you switch off everything that will keep the atoms in this container. The atoms just fall down, and falling down, they will expand. And from the expansion dynamics evolution, you will get that, for example, the momentum distribution and then the temperature of the cloud. And this is important because this, in some sense, will tell us a lot about the system that you have cooled down. Okay, so now I told you that we can cool down the system. So just to summarize, we start with atoms at room temperature in a setup that are more or less complicated. This system is cooled down by laser cooling. So we imprint lasers in 3 directions, and by scattering of the atoms, the photons by the atoms, then the system is cooled down to microkelvin. Then this cloud are trapped in additional potential, can be magnetic or can be optical. Then you evaporate the atoms, for example, opening, so decreasing the container wall or using microwave or radio frequency photons. And then the system becomes colder and colder. That means that, again, in the picture that I gave you at the beginning, this means that the de Broglie wavelength becomes comparable with the mean interparticle spacing. So interference effects start to become very important, and that means that quantum mechanics or quantum behavior should happen. And indeed, when this happens, you will see that the way in which this show, for example, is in an abrupt change in the image or absorption imaging that I was showing you at the beginning. So this is a cloud, I think, of rubidium that has a temperature that is larger than this critical temperature that, again, corresponds to a point where the Broglie wavelength becomes comparable with the mean interparticle distance. And in the time of flight picture, if I do this and I just recover the absorption imaging on a CCD camera, I will see that the momentum distribution is nicely fitted by a Gaussian. This is in fact correct because you expect Maxwell-Boltzmann distribution to be super valid. And so from this kind of distribution, we extract also the temperature and not only the number of particles. But if I cool down, again, this is a case of rubidium-87, so it's a bosonic atom. What happens is that you see that the momentum distribution changed dramatically. And I mean, for sufficiently low temperature, the momentum distribution change become very peaked and the density becomes very, very high. This that I just tell you like a fairy tale, this is just the transition from a normal gas to a Bose-Einstein condensate. Okay, so this cloud corresponds to most of the atoms in a single occupying the lowest single particle level of, in this case, harmonic trap potential. Of course, this was one of the breakthrough of the last, I would say, 30 years of physics, and in fact was awarded by Nobel Prize. And this is the science cover corresponding to an experiment by Rick Cornell at Gila in the United States, in which exactly they were providing us the transition from a Gaussian distribution to a Bose-Einstein distribution by cooling down the system to ultra low temperature. Well, the first thing that I want to show you, because I decided to give you some example just to show you how, I mean, the transition from the description that you can have of particle or real balls that is moving in space to wave, I think that can be really shown nicely by an experiment that is the same experiment that you can do with photons in a laser beam. So as you probably know, without entering too much in the detail of of the fact that even a single photon can provide interference pattern, but just consider a source of a laser beam, so a source of many photons. These are two slits, and when you then go to see what happened in a screen placed after the two slits, you will see that the intensity that you recover is not just one line, but is a set of lines that are separated by black region. This is nothing else than the double slit interferometer or interference pattern that you can get using, again, laser light passing through two apertures. I mean, this is the example in the cartoon, and this is exactly what you see in the screen. So the first thing that you can ask yourself, okay, if, Giacomo, you are telling me that the atoms become a Bose-Einstein condensate, become so cold in general that they are like waves. So what happens if I repeat this experiment or analogous of this experiment with Bose-Einstein condensate? Well, what is possible to do, and this was done by Wolfgang Ketterle the first time at MIT, is that he was splitting a Bose-Einstein condensate where then these atoms were released from the trap, and then they were observing exactly where the two clouds were superimposed in time of flight. You were observing, in fact, the same thing that you can observe with the laser with photons, so is an interference pattern. But the only thing that you have to take into account, this is an interference pattern given by sodium atoms. So these are matter wave interference. So are not photons that are interfering, but these are really matter waves, atomic matter waves. So this was the first demonstration that, in fact, we were dealing with something that is very special, that is coherent in some extent. You will see how also in another experiment I'm going to show you. That is the analogous, if you want, of what laser is for photons. Okay, so despite some difference, of course, due to the interaction between the atoms, people started from that point to consider Bose-Einstein condensate the analogous of a laser, so an atomic laser, if you want, from the point of view of the coherence and some other properties that are associated typically with laser light. So, as I was saying you at the beginning, that anyway, you have also another class of particles, the one with integer spin, that are called fermions, that follow a completely different distribution function. And the question, of course, is, can you cool down also Fermi system? Of course you can. I will not enter the detail of how you do, because typically it's more complicated, but in principle you can. The only message that I want to give you is that the transition to Fermi degeneracy, that again corresponds more or less to the same point in which the Broglie wavelength is associated to particle becomes comparable to the size, to the distance between the two particles. That is a little bit different, so it's not a phase transition. And in fact, is not such spectacular. I mean, you can compare what happened in the case of Bose-Einstein condensate to what happened in the case of Fermi gas, and you will see that even from the point of view of the density distribution in the momentum space, if you want, there is no such big difference. Okay, so anyway, that is just the message that I want to convey. Of course, you can cool down as well bosons and fermions, even though with fermions, situation is more complicated, and to extract the properties of the Fermi degeneracy, you have to use specific tools that you must, for example, a specific thermometry that is not used for in the case of Bose-Einstein condensate. But anyway, everything works. So the first thing that people can ask is, and many people ask me, in fact, about this coming from other field of physics, some friend of mine, for example, doing other kind of things, why Bose-Einstein condensate are so special? Well, the point that I want to give you is that, of course, this is a macroscopic object, because despite, I mean, of course, we don't have a massive 1 meter Bose-Einstein condensate, still Bose-Einstein condensate can be as such large as alpha millimeter. Okay, these typically are scales that are achievable, depends of course on the trap and on the number of particles. So these are really macroscopic quantum objects. They can have really long lifetimes. So if you do things in a proper way, and the lifetime of Bose-Einstein condensate in an optical trap, for example, can last more than 10 seconds. So it's something that is not evanescent, so means that also the exploitation of this object can be done quite nicely. We don't have to work at ultra fast timescale, ultra short timescale, but we have like seconds to work with. And again, this is means that you can handle that in a simple way. Okay, so this is a special object by the definition, and so in fact people can did them and still are doing many nice experiments. One thing that the first thing that I want one thing that, for example, one example that I want to convey you is that, of course, typically, and with the Bose-Einstein condensate, or in general with the pairing between particle in a Bose-Einstein condensate-like state, is associated to some properties that are very special. Okay, one of that is the possibility to flow, or to flow in general without resistance or without dissipation. And this is what happened, of course, also in the case of other kind of system in nature. And these two properties are called superconductivity, or superconductivity and superfluidity. And again, I don't have too much time, of course, and these again, I think that are still detailed, but these properties are related to the fact that particles anyway have to interact. Okay, so this will not be true, for example, for particles that do not, for ideal gases, for example, this will be very not possible to have this kind of properties. Okay, just to give an idea of something that probably most of you know, I mean, also in general, without doing complex or advanced quantum mechanics or physics courses, is that if you take a metal, and you let some current flow inside the metal shows resistance, okay? And this you can associate it macroscopically by the fact that if you take a piece of metal in which current flows, I mean, of course, with some care, typically you will touching this metal, of course, you will feel that the metal becomes hot. And the fact that it becomes hot is due to the fact that electrons that flow inside the metal, of course, have to interact between they scatter impurities, scatter between themselves, and they produce heating. Okay, there is a dissipation. And this is encapsulated in this quantity that is called resistivity. Okay, if I consider a normal metal and I just plot the resistivity versus the temperature, you see that what happened is that the resistivity will never go to zero, but will follow actually this kind of curve. Okay, without entering too much in the details of which kind of dysfunctional for with the temperature, you see that at low temperature, where temperature in fact is zero, still there is some scattering, and this scattering creates and gives rise to a finite resistance. Okay, this is typically what you expect for normal metal. Well, for superconductors, this is not the case, because what the people have seen is that for superconductor, of course, you have still a decrease of the resistance, of the resistivity decreasing the temperature. But when you arrive to a specific value of temperature, the resistivity drops completely to zero. Okay, so this is a special system in which cool down to below critical temperature, the system can allow the transport of electrons, in fact, not electrons, but a pair of electrons, without any resistance. And associated to this, I give you two examples. These are taken by YouTube. You have like very special properties, like, for example, again, no friction or resistivity, no viscosity. Then in the case of a magnetic field, in the case of superconductor, you have a full expulsion of magnetic field, so there is the Meissner effect. So there are specific properties that are associated to the cooling down of the system below critical temperature, where the quantum nature becomes evident. And in particular, in both cases, Bose-Einstein condensate phenomena show up. Okay, just to say how the one that in fact discovered this 1913, that is Kamerlingh-Ohm, said, so he was really showing, actually measuring, that below a critical temperature, that in this case is 2.2 Kelvin, okay, the viscosity of the system was in fact going to zero, okay, was decreasing quite a lot. And already at that time, he was saying that such an extreme, situation could be possibly be connected with the quantum theory. And in fact, this is the case. And okay, these phenomena that are really quantum phenomena, really spectacular, pure quantum phenomena, show up in different systems in nature. And again, here I just give some example, an example given by helium, by superconductor, by nuclei, neutron star, and of course, also in atomic Fermi and Bose gases. Well, the take-home message that I want to deliver you is that if you consider a bosonic system, typically, okay, Bose-Einstein condensate, for sure in 3D, is definitely associated to superfluidity. Okay, so in 3D, if the system is a Bose-Einstein condensate, then it will show up also superfluid nature. For Fermi system, the situation is a little bit more complicated because, in fact, you need to have some extra ingredient that, in fact, is to consider two kind of fermions or two spin or two internal state of fermions, okay, that must be in some way connected, pair, and then becoming pair of fermions means that are like bosons, so become like cool down, become like a Bose-Einstein condensate of Cooper pairs, actual pairs, and also for Fermi gas, this means that you can access the superfluid nature. Well, in general, it is possible to probe experimentally this kind of state using different techniques. One technique, for example, that in fact probe definitely the condensate nature, so the fact that the system is condensed and show some superfluid nature, but mostly this is a probe of condensation, is the Josephson effect. Okay? To probe, then you can also observe in this kind of system the fact that you don't have viscosity and resistance. You can study how, if you imprint a current in annular geometries like this is the case of atoms, this is the case of a superconducting ring, you can observe the current to flow almost without any dissipation. And in the case of superconducting ring, what happens is that the current can flow per years, okay, without stopping, without any decay. Or, and this is the other possibility, you can see how the system, in the case of atoms or helium, is responding to a rotation, form quantized vortices that are just these holes happening in the superfluid, or in the case of a superconductor, if you apply a magnetic field in type 2 superconductor, you will see also in this case the formation of vortices. So these are the probes that allow you to say that the system below critical temperature, again, is a condensate and superfluid. Well, for sure, vortices are one specific case, because as said by the Nobel Prize in physics, actually Eric Cornell, the first one that could bring down to Bose-Einstein condensate a gas of rubidium, anytime you think about superfluidity, you have to think about vortices. So now I want to give you an example of how it's possible to do this in the case of Bose-Einstein condensate in general. So if I now rotate a superfluid, so I can use some trick. For example, I take my cloud and you see my mouse, I can start to steer with a spoon-like, I mean, done by optical means. I can try to spoon my condensate, or in case of a magnetic trap, I can really rotate physically the potential, and then this means that I will transfer angular momentum to the cloud. Well, what happened, again, is the formation of vortices, and these vortices, anyway, are special because they can assume in the circulation, from the circulation point of view, only quantized values. Okay? So that was both for Bose-Einstein condensate and for superfluid Fermi gas, the direct proof that the system is superfluid. So the formation of this array of quantized vortices was the demonstration that the system may show macroscopic quantum phase coherence, so that is really a superfluid and condensate. And this, again, is the experiment done by MIT, in which they were using two laser beams that were steering the BC, or in this case was a superfluid Fermi gas, and at the end, they observed the deformation of quantized vortices. The other experiment that you can try to do to show that is to take the system and bring in annular geometries. Okay, because again, the fact that the system can perform persistent flow, this allow you to say that the system, in fact, is a superfluid. Again, there are experiments. I don't want to bother you with the detail of these references, but just want to give you a demonstration. So what is possible to do is to bring these atoms inside this ring potential. So these are atoms in a ring geometry that can have different sizes. And by just shining an additional laser beam, you can imprint current in the annular geometry. The message that I want to give you, in fact, is not related to this specific case of how we detect the current, the circulation, but that a system of atoms in a ring geometry will show that the current that, in fact, you can imprint on this system is quantized. Okay, this W is just the winding number that tells you how many H over M you are imprinting to the superfluid. And you can see that this is quantized, so you cannot imprint all the velocity in the system, but only quantized velocities. And again, the quantization of circulation in a superfluid has to match with the quantization that you observe, considering, in this case, superconducting ring, in which what is quantized is the trapped magnetic field flux inside the ring, that also, in this case, is quantized as the current in a superfluid in a ring potential. So the last message that I want to give you, why we think that these systems are useful and for what people like to use nowadays. So as said, we produce a bunch of atoms that are very, very cold. They are superfluid because they are condensate, and they are macroscopic quantum objects. What we can use this system for? Well, at the beginning, people really started to think to implement the concept given by Richard Feynman, that in some sense, in many papers, in fact, try to propose that to simulate a quantum system or a quantum phenomena maybe was better and more efficient to use a quantum system, okay, a quantum system itself, that maybe is different. So this is the idea of quantum simulator. Then, of course, people went even more and defined the concept of a quantum computer that just use quantum system, for example, ultracold atoms, ultracold ions, can be, of course, superconducting qubits, to create the next generation of computer that are called quantum computer, okay? So computer that use quantum mechanics law to perform calculation in a much more efficient, incredibly much more efficient way. Okay, the idea that is behind the quantum simulator, again, I want to show you this slide again, is that you can trap atoms inside the structures that you can realize with light. Meaning that you can create lattices, as I showed you at the beginning, you can create a disordered potential, or you can create even much more exotic configuration, like, for example, hexagonal lattices that in some sense represent or resemble the situation that you find in graphene. Okay, but in this case, the advantage of using light and ultracold atoms is that you can mix, for example, disorder in a graphene, like potential, or you can use disorder in a regular potential, meaning that in one system you can study the pure and ideal case of graphene, or the situation in which graphene potential is together with disorder. So you study how the effect of disorder can alter the properties, the special properties of hexagonal potential. Well, what people can do in the lab then is to use laser light, to create different kind of geometry and different kind of structure. And for example, and this is what Patricia said about me at the beginning, you can study quantum transport phenomena because, of course, you can engineer a structure, you can engineer a circuit in which instead of electrons, you have atoms. And the funny thing is that, of course, you can shape the potential like you want. Okay, this is funny, but this is more serious, and this is even more serious. These are taken from my lab, and we can study structure like ring, like I was saying at the beginning, but also you can study something that is more exotic, like a ring with some defects that are around, to study some other kind of mechanism or some kind of phenomena. The other thing that we can do now, and this again is from my lab, we can trap, for example, a bunch of atoms inside this potential. Okay, these are all atoms. These are 100 atoms that are inside inside this lattice potential again. But the nice thing is that you can control dynamically. So you can take your atoms that are in these wells, and then you can bring together. You can then remove. You can interact, let them interact together, and then you can resplit out. Meaning that everything that you can do now is controllable at the level of course, single atom. These are 100, but of course, we can also tune to much less. There are experiments working with 1 atom per site. We can image the atoms at the level of single particle. And you can let them, for example, interact and to study, for example, gates, quantum gates for quantum computing, or you can study, for example, spin Hamiltonian or different kind of Hamiltonians that typically are very complicated to treat numerically by theory. This you can do directly in the experiment. So the experiment will give you exactly the implementation of the Hamiltonian. Well, that is more or less my last slide, because I think that the message is the state of the art now is the following. You have cold atoms. These atoms are in optical structure. This an example is a regular lattice, but you can, again, you can have a toroidal situation, you can have hexagonal potential, you can have anything that you want. Then the atoms are manipulated and imaged with very high resolution, because now people also in the ultra-cold atoms community start to put microscope objective, the same that, for example, in biophysics are used by years, of course, but you can use microscope objective to see the single particle. And this happens in real time and in reality, because this is an image taken by the group of Marcus Grein in Harvard, and you can see that every of this square is a single atom that is fluorescing light. And so this is a bunch of single atoms that are interacting. And from the analysis of picture like this, of course, by changing temperature, changing the density, changing the spin component, of course, you are able now to reproduce and to really implement Hamiltonian that are very complicated to be solved. Actually, some of them are impossible to be solved by numerics. For example, and this is a name for you students, is the Fermi-Hubbard Hamiltonian. This is expected, for example, to describe high-TC superconductors that still are, from the point of view of modelization, unsolved. Okay, so the message is the following. You have an Hamiltonian. So Hamiltonian is just a model, a physical model that you want to describe. Maybe some of these models are impossible to be solved by theory because it's too complicated, too many particles, too many degree of freedom. So what people now are doing is to take this Hamiltonian, design optical potential, cool down the system, and then see how the system, changing some parameter, evolve to something, to a ground state, to a superfluid state, or to a rotational state, whatever. Okay? This is the direct implementation of the Hamiltonian. And of course, this now, just to give you the idea, ultra-cold atoms quantum simulator are leading experiment, of course, giving results that theory have now to explain. So the quantum simulation is more advanced than the theory from which this experiment or this implementation was done. Okay, so the theory now use quantum simulation output to perform it better and to give better or more advanced result. Okay, the last slide. So I think that it's worth to read this because this is is a very specific case in which Martin Zwiela and MIT was observing superfluid dynamics in ultra-cold Fermi gases. Okay, and what he said that we observe superfluid flow in an expanded Fermi gas down to density to about 10 to the 11 centimeter to the minus 3. At this density, the average distance between two atoms is 2 micron. Well, now it just compare and do a very strong link, saying that the average distance between neutrons in a neutron star is a few femtometer, 10 to the minus 909 micrometer, corresponds to density of 10 to the 38 centimeter to the minus 3. This nicely illustrates how general the phenomenon, for example, of superfluidity is. So this means that we can reproduce in our lab things that are not only related to our lab, to these quantum gases, but to something that is completely very, very general, that touch many, many different fields of physics and systems, even the ones that are super far and, of course, in which we just speculate the properties. Okay, so I would say ultracold atoms are macroscopic quantum system in which probably, this is me, maybe 30 years ago, that maybe I was studying quantum mechanics and I was thinking that this quantum mechanics is something that, of course, is very nice, but untouchable. Well, ultracold atoms just bring the quantum mechanics to a point that you can touch the properties, you can touch the effect. And so I would say that this is really a lot of fun. So I really thank you for your attention.
Thank you, Giacomo. So we have some time for 2-3 questions. Yes? So any questions in the audience?
I actually have a question. So you mentioned about cold atoms to be used for quantum computing, but do you actually can use cold atoms for computing? Like how is this can be applied since you have to cool the system for a long time? You mentioned that these cold atoms can last for 10 seconds, for example, a condensate or these systems. So can we foresee a system that can last for longer so that it can be used for actual computers that can last for more than a few seconds or 1 minute for calculations?
Okay, so that is if you want, I just tell you what is happening now. So people now are cooling down system and they trap in the so-called optical tweezer. Okay, so these are just, and you don't have to be degenerate, in fact, you just take a MOT, so cloud at microkelvin, and then with this optical tweezer, you isolate a single atom, okay, in this array. And this tweezer, of course, have the degree of freedom to be movable, okay, so you can really put the atoms together. And actually what the people do even to do a next step, that is to transfer this atom in a Rydberg state, in which the interaction between the atoms is very long range. Of course, you say something that is right. So now I must say that using cryogenic technique, this tweezer can arrive to lifetime of more than 60 seconds. But what is important, I would say, is not how much does it the system live, but how fast are the operations that you want to do. And for example, for Rydberg atom, they can use they can make some quantum gate operation at the level of hundreds of microseconds. So I think that what is important is to consider how fast you must be, and also related to the if you want, from the point of view of the coherence of your state. Okay, so if the system is coherent enough time, and the operation time is fast, then I think that you are still safe. But again, there are other systems like photons or superconductors for which this operation can be more efficient. I agree. Okay. Just 1 second. Okay. Oh. I am here. Just someone just not at my door, so I don't know who is. Okay, please.
Okay.
Okay.
So thank you. Do we have any questions from the audience? Otherwise, we have a question from YouTube. Our colleague here, Professor José Abel Hoyos, he says, simulating spins Hamiltonians or other interesting models such as Hubbard is a promise that so far that it's not fulfilled because temperature is still high compared to interaction. What are the experimental problems for diminishing the temperature? Are there fundamental problems, or one needs a breakthrough, or this is this is hoped to be accomplished in the near future?
No, so okay, I thank you for the question. So I must say that now in the Harvard group of Marcus Greiner, they are reaching temperatures that are very, very low. And so they observe so far the antiferromagnetic ordering in this repulsive Fermi-Hubbard. And I think that they are working, I know because I met the guy very recently, they reach now, they are implementing some scheme that in some way stabilize the laser even more. And I would say I'm quite optimistic on the fact that soon we will get very, very nice results about the implementation of the, actually to the ground state of the Fermi-Hubbard model. So this is purely technical, is due to the noise of lasers, but people are working on that, stabilizing as much as they can the schemes to get the lowest entropy per particle corresponding to the onset of the superfluid state in the Fermi-Hubbard Hamiltonian model.
Okay.
Any other questions?
The audience?
No?
No.
So, Giacomo, we thank you again. Thank you very much.
Thank you, and sorry for the rush.
No, it's okay.
Okay, so let's thank the speaker again once more. So,
Now,
yeah.
see you soon.
Sim, claro, claro.
Pessoal, já que tem alunos aqui começando a carreira, né? Bacana a palestra do Giacomo. Só queria dizer que aqui no Instituto nós temos vários professores, tanto teóricos quanto experimentais, nessa área. O Giacomo talvez não estressou muito, mas os átomos frios, eles tocam todas as áreas desafiadoras da física moderna. Quebra de simetria, problemas de sistemas que chama altamente correlacionados. Né? Os átomos frios permitiram mostrar que superfluidez, supercondutividade é o mesmo fenômeno. Então tem muita coisa e, obviamente, ninguém está forçando vocês a fazerem átomos frios, mas vocês vão ser físicos, é uma boa oportunidade para visitar os laboratórios. Nós temos aqui relógio atômico com o professor Daniel, tem átomos frios e espalhamento de luz com o professor Felipe, nós temos sistemas de duas dimensões que a Patrícia está montando, tem condensados fora do equilíbrio, que é um desafio da física moderna, como que sistema quântico, né, quando está em temperatura finita, como que ele sai do equilíbrio, como que ele volta. Nós temos o Marcassa fazendo átomos de Hilbert. Então nós temos vários laboratórios aqui, que eu acho que vocês devem visitar para conhecer, não é? Porque é uma área importante, uma área que vem dando prêmio Nobel sucessivos aí ao longo das últimas décadas. Né? Como são alunos iniciantes, né, diretor? Eu achei importante dizer que isso está bem próximo da gente aqui, que vocês podem visitar. Obrigado.